Good morning, chemistry students. My name is Mr. Adam. This is chemistry. Today is the 27th of April. It is a Monday. Happy Monday, everybody. And it is day 3 in our rotation. So welcome to day 21 of online learning. I know it's hard to believe, but it's actually been over 4 weeks since we started this online learning process. It's been a month of this online learning. So it's kind of crazy to me. It's kind of hard to wrap my mind around. When we first heard that we were leaving school for a little bit for the COVID-19 pandemic, we thought we'd be back within a month. So we thought we would be back in class by now. We thought we would be back together after this month-long break, and yet we're still here. We thought we would have had a spring break by now. We thought the schools would be reopened, but they're not. But what's crazy about humans, what's so unique and so special about humans is that they're able to adapt to these crazy circumstances and these crazy situations. So I know it's not been easy, but I'm proud of each and every one of you for being able to adapt to these changes, for being able to adapt to circumstances that aren't quite ideal, to not getting to be with your friends, not getting to be in school, and actually learn things in person and with your teacher and with your students and your classmates and everything. So I know it's been difficult, but thank you so much for adapting. And I know that you're going to continue to do so, and that this in the end will be a lifelong lesson that you are capable of anything. That even when the circumstances, the situations get really bad and really weird and really different, that you can deal with those changes. Because remember, we can't always control what happens to us. We can't control what happens in the world. All we can control is how we react to it, right? So all we can control is our reaction, how we react, how we emotionally react, how we physically react, and what we do and how we treat the people around us and how we treat ourselves. So remember that. Treat yourself kindly, treat others kindly, and know that even though it's been difficult, I'm proud of how each and every one of you has adapted to these changes. Okay, so with all that being said, we have a lot to cover today, but one more quick announcement for the day. I am going to start doing virtual office hours. I've heard of a couple other teachers who are doing this, and I thought, yeah, that's a pretty good idea. So I'm going to start doing virtual office hours from 1:30 to 2:30 every day, Monday through Thursday, because Friday we'll still do our chats if anyone shows up to those. So that means from Monday through Thursday, I will be in a Google Meet call from 1:30 to 2:30. It might just be me chilling, doing my own thing. It might be other people who come on for help. But if you need help, if you have questions or actually need to talk to me in person about an assignment, about something you're confused about a concept that didn't quite make sense to you, that is your opportunity to come online, ask a 5-minute question maybe, or maybe we'll talk for half an hour about something, about Lewis structures or something like that. But it's your opportunity to come get help from me in person because you actually need something explained to you in person and not just, through a video or through a reading or through notes or anything like that. So that'll be from 1:30 to 2:30 every day. Come on, to chat, to ask a question, just say hi, whatever you need to do. There might be people there, there might not be, but I'm always there for you during those times if you need help or need to ask questions. So there will be a link, permanent link on our Google Classroom to a Google Meet, and I will be there from 1:30 to 2:30 every day. If you need to ask a question, jump on there, come say hi, and we'll work through it real quick, okay? So that's going to be the virtual office hours from now on, from 1:30 to 2:30 every day. And they'll start today, so I'll be online from 1:30 to 2:30. So, like I said, today's lesson, we have a lot to talk about. So let's get down to it. So today's lesson is on these things called electron domains. So, that's a weird thing. I don't know what those words mean. So let's think about it for a second. All right? So we know what electrons are. They're these little tiny negatively charged particles, and they zip around, they go around in an atom, right? And they're always moving, and they're always moving quickly. So we know what electrons are. What is a domain? Where have you heard that word before? I hope most of you have heard it in math class, right? So in math class, the domain is where the x variable is, right? It's what two numbers it's between. It's essentially where that x variable lives or where it resides, right? The general area that it is in. Okay, so that's what a domain is. If you think maybe in like historical context or in the time of kings and queens, right? A king's domain is essentially their kingdom. It's where they rule. It's the area that they have domain over or command over, right? So a domain is a place where you have influence or where you exist or where you live or where you control, right? Okay, so with that being said, let's think about where electrons live. Do you remember these things called orbitals? If I say that word to you, does that make you nervous? Does that bring back memories and pain? Trying to understand what orbitals were and orbital diagrams were? Don't worry. Just two things you kind of need to remember about orbitals. Number one is that orbitals generally are pretty spherically shaped, right? So they're just kind of a sphere or kind of a ball or a circle where electrons live, right? Electrons are zipping around and around and around, and they exist basically in this sphere. Okay, that's one thing you need to remember about electron domains. Two, electron domains have the same charge as electrons, right? So let's think back. Protons are positive, neutrons are neutral, electrons are negative, right? Electrons are negative. So if you have an electron domain, it is negatively charged. So now what do we know about things that have similar charges, have the same charge, right? They attract or repel. Opposites attract. Similar charges repel each other, right? So if I have two electron domains here, two circles here, what's going to happen when I try to put them together? Can I put them in the same region? Can I smash them together? No, right? What happens when I try to put them together? They repel each other, right? Because they have an opposite charge. Or I'm sorry, they have the same charge, so they're repelling each other. So two electron domains are negative and they repel each other. So if you have two electron domains, they're going to repel each other, and they're going to try to get as far away from each other as possible, right? They try to get as far away from each other as possible, but they're still connected by some sort of atom or something, right? So if they're getting as far away from each other as possible, they're going to form a straight line. They're going to be about 180 degrees apart from each other, right? Okay, that's if you have two electron domains. They're repelling each other to get as far away from each other as possible. Now what happens if you add another electron domain? What happens if you have three electron domains? Again, what are they trying to do? Repel, get as far away from each other as possible. So you'll see if you have three electron domains, my hands kind of screw up the equation a little bit, but that's okay. If you have three electron domains here, 1, 2, 3, they're going to get as far away from each other as possible. What kind of shape are they forming? Like a triangle, right? They're about 120 degrees away from each other, getting as far away from each other as possible. And even if you push one towards the other one, it's going to push the others away, right? Okay, so three electron domains get as far away from each other as possible and form kind of that triangle shape. So now what happens if we have Mr. Adam try to hold 4 balloons in one hand? If we have 4 electron domains here, right? There we go. If we have 4 electron domains here, what's happening? They're again trying to get as far away from each other as possible. And so what you're going to see is you have 3 balloons here, and this one is kind of moving towards the back. It's not forming a square shape with 90-degree angles, but one is actually going towards the back in kind of this 3-dimensional shape. And this shape is what we call tetrahedral, right? So in this, you have still a kind of triangle in the front, but one atom or one electron domain in the back trying to push away. And this, what's kind of cool is with this is if you try to push one towards the other or try to push this back one, where's the back one? There we go. This back one towards the front, it pushes those others away. So there's always one in the back, right? Forming that shape where they're all trying to get as far away from each other as possible. So electron domains repel each other, try to get as far away from each other as possible. And it very much matters how many electron domains you have to see what shape is going to result. So why do we care? Why do we care about where electrons are, or why they're repelling each other, or where they exist, where electrons reside? Simple. If we're looking at molecules, right? Molecules are just atoms bonded together, and atoms and molecules are connected by what? What is a bonded pair? What are atoms bonded by? A bonded pair is 2 atoms sharing electrons, right? So if they're sharing electrons, what we're saying is atoms that are connected together in a molecule have electrons between them. And those electrons are trying to repel each other. They're trying to get as far away from each other as possible. And that is what gives our molecules an actual shape. So if we're looking at the shape of molecules in this whole section 2, we need to know why molecules form certain shapes, why electrons are trying to get as far away from each other as possible, and what shapes result from that. So we're going to look at 4 molecules today, okay? So our first molecule over here, let's focus on this one right now, is CH4, right? So CH4 here, you can see is 1 C in the center and 4 H's on the outside. You could draw a Lewis structure for that very easily, and you would see that there's a C in the middle and 4 H's bonded, each by 1 bonded pair. Now I drew lines instead of the electrons here, but know that the line, the one line, is again just a set of electrons, a pair of electrons, okay? And I've circled each of the bonded pairs in purple, which, okay, you can't tell the difference between purple and black. I've circled each of the bonded pairs in purple, okay? So 1, 2, 3, 4 bonded pairs in purple. So if I were to look at a molecule of CH4, it would look just like this in real space, where you have 1, 2, 3, 4 bonded pairs and 4 atoms around that C, right? Okay. So let's look at this 3D molecule right now, right? We see those 4 bonds, we see the 4 atoms. What is the, how are they kind of shaped around this molecule, right? How are the atoms spread around this molecule? Well, if you look, just look at this. There's a kind of a triangle pattern again, but it's kind of a 3D triangle, right? It's kind of like a pyramid. And if you have that triangle, there's still 1 atom in the back. So again, these atoms are trying to push away from each other. These electrons are trying to push away from each other as far as possible. And so you're going to see that it forms this kind of tetrahedral shape where there's kind of a triangle, 3D triangle pyramid in the front, but then there's 1 in the back sticking out, right? So this is what we call a tetrahedral shape. And this is if you have 1 atom in the middle and 4 bonded pairs around it, or 4 atoms bonded to it, right? So that's CH4. It forms a tetrahedral shape, which you'll read about in your reading today. Our second molecule here, this is NH3, right? Again, you could draw the Lewis structure for NH3 very easily. You're going to see that N likes to form 3 bonds because of honk 1, 2, 3, 4. So 1, 2, 3 bonded pairs, but it has a lone pair on it. We know that because of the Lewis dot symbol. So it has 1 lone pair, right? And 3 bonded pairs. So if we're looking at a molecule of this and the 3D shape of this, we're going to see, again, there are 4 electron domains around it. But in this case, we have 1 lone pair, which isn't bonded to an atom. And with lone pairs, for our purposes, they're kind of invisible. They still exist. They're still pushing other electrons, other bonds away from them, but we don't really see them. So what I'm going to do is I'm going to cover up this lone pair. It's like it doesn't even exist when we're looking at this, okay? So when I look at this, what kind of shape does this take on? Again, it looks like a triangle, but if you look at it in 3D, you'll see that this lone pair here is pushing those atoms, those bonded pairs away. And so it's kind of a 3D triangle, right? If I set it on the table here and look at it, oh, there you go, right? It looks kind of like one of those big things in Egypt, one of those natural wonders in Egypt, not natural, man-made wonders in Egypt, that we call the pyramids, right? It looks like a pyramid. And so it's a triangle pyramid, and so we call that trigonal pyramidal, which literally just means a triangle pyramid, right? Okay, so that's when you have 3 bonded pairs and 1 lone pair on top. All right, our next molecule here is H2O, water. It's something you should all be very familiar with, be able to draw the Lewis structure for it very easily, okay? 2 bonded pairs, circled in purple, and 2 lone pairs. So all we see is that it's bonded to 2 atoms, and we don't see those 2 lone pairs, but they still very much exist, and they're still very much pushing the bonds away from them, right? So if we look at water here, I've covered up my lone pairs. They exist here, but I've covered up my lone pairs. What does the shape of this molecule look like? Well, you have 2 bonded pairs, right? Are they in a perfect straight line? If you look at them this way, they look like it. But they're not really straight across from each other, right? They're being pushed down by these lone pairs. What do they look like? They look like they were a straight line, but they were just bent. So this is the shape that we call bent. So if you have 2 bonded pairs and 2 lone pairs on top that you don't see, then you form this kind of bent shape, right? Easy enough. So water is a bent-shaped molecule, and that's going to be really important for biology and for what we talk about in chemistry with these things called intermolecular forces, for why water behaves the way that it does, why it freezes at a relatively low temperature, and why it's in the liquid phase all the time, most of the time. All right, last molecule we have is HCl. So H bonded to Cl, there's only one bonded pair, which makes sense because it's only bonding. Cl is only bonding to H, only one bond between two atoms. And there are 3 lone pairs on Cl, okay? So what we're looking at here is actually the Cl, and then the H is over here. And there are 3 lone pairs, which again, we're going to cover up. This shape's really easy, right? So if you look at this shape, I'll just cover up like this. That's a lot better. If you look at this shape, there's just one bond. No matter which way you put it, what is there between these 2 atoms? It's just a straight line, right? So this is just a straight line. No matter which way you look at it, if you look at it in 3D, it's just a straight line connecting those 2. Because those 3 lone pairs you can't see, you can only see the bonded pair, the straight line connecting them. And so this shape, really easy, a straight line, is called linear, right? So those are the 4 basic shapes that we have for molecules. What you're looking at when you're looking at shape is how many bonded pairs you have, which you can see, and how many lone pairs do you have, which you can't see. They're all repelling each other. They're all repelling each other into this kind of tetrahedral shape. But if you're not looking at one of them, you can't see one of them like this, right? Then it looks like a different shape. Take another one off. It looks like a different shape because you can not see those lone pairs. You can only see the connections between the atoms, those atoms forming that general shape. So you're going to learn about those today, a little bit in the reading and the notes, and then go ahead and do the assignment tomorrow about molecular shapes, about electron domains. And you'll keep learning about molecular shapes. You'll keep working with this concept of tetrahedral and trigonal, planar and linear and bent and all that good stuff. So make sure you're good at this. Make sure you master this. If you have any questions today, I will be available from 1:30 to 2:30 on my virtual office hours. Come to Google Meet, show up, ask some questions. We'll work through some stuff. It'll be great. So I hope to see you there. If you need some help for the share of the day, bringing it back to what we were talking about before. What's one way that you have adapted to all these changes? What's one way that your ritual has changed or that you've had to adapt? Maybe how you've had to live with your family, maybe what you do every day, what your routine is, how that's different. How have you adapted? Because this hasn't been an easy change. It hasn't been simple for any of us or easy for us to get along with the people that we're living with. But how have you best adapted to suit these changes, to suit these times? I know for me, I've had to be around my roommates and my girlfriend all of the time, so I've tried to help out by maybe cooking for them or offering to do some grocery shopping for them, picking up things for them, trying to do the dishes and take care of the house and everything. So how have you adapted to these difficult times, to these changing times? Let me know today. And like I said, I'll be around for virtual office hours if you need me. So hope to see you there. Thank you, everybody. Let's get a 1, 2, 3. Clap on me.